Okay, and section 5.3 is simply taking 5.1 and 5.2 and really looking at a little bit more math involved. In chapter 6, we're going to get into friction and coefficients of friction, and then we're going to get into air resistance. We're going to look at other specific or special types of forces, like even circular motion, right, with centripetal force we're going to talk about, but that's all chapter 6. So chapter 5 is like an intro to forces still. But 5.3 is really where we get into some of the problem-solving techniques. So I'm going to start with, this is problem on page 108. This is sample problem 503. So we're going to start with this one first. And what we're going to do from here is we're going to go through each of these one at a time. So let's take a quick look at what it is. Here's the problem itself. All right, there's the problem itself. I think a diagram is given, so I'm going to put the diagram next to it also. Obviously, if you have the electronic version of the book, you could be viewing this as well.
It's the same thing as last time. With the
Is it happening again?
image.
Oh, man. I don't know.
Wait, which page was that on?
So this is page 108. Any better when I do that? Yeah, there we go. It's a little bit better, right? Okay. So let's take a look at what's going on here. So first, the figure on the right shows a block S sliding with a given mass. The block is attached, it's free to move along the horizontal frictionless surface. And that happens on the test a lot with multiple choice problems. A lot of the time, multiple choice problems will involve something that's frictionless because it's less work for you to do, and it's a multiple choice problem. If friction is involved, it'll probably be either they'll give you the force, so you don't have to worry about mu Fn, or it'll be a problem all about friction, and then you have to actually solve. But if you're given a lengthier problem like this, in a multiple choice type problem, it would most likely be frictionless. Frictionless surface connected by a cord that wraps over a frictionless pulley to a second block H, called a hanging block, with a mass given of 2.1. The cord and pulley have negligible mass compared to the blocks, meaning they are massless. Later on, we'll talk about what if the cord and the pulley have mass, and that does affect the answer. But that's not until chapter 7 or 8. The hanging block H falls as the sliding block S accelerates to the right. First, let's talk about this problem. Let's write down something in big letters at the top. Big letters here. If there's tension in the rope, the system moves with the same acceleration for each block. If there's tension in the rope, the system moves with the same acceleration in each block. That's a really important point to make. It's as if they're moving together. Every inch that the block H falls creates 1 inch of motion horizontally for block block S. So what's going to happen for all of these problems is you're going to notice that as we go through them, you're going to assume that the acceleration of this one falling is the same as the acceleration of this one sliding. Now, one of them will be an AX, that's block S, and then block H will have AY, vertical acceleration. Okay, so keep that in mind as we go through these types of problems.
So what would be another example, not on a pulley, something else,
They weren't?
Where there'd be tension and they wouldn't move with the same acceleration.
It's only if there's not tension that this won't happen. So when there's what's called slack in the line, so imagine the cord is on the ground. The first one moves, then tension engages. So the entire beginning part, when it's moving by itself, the other one isn't moving. So whenever there's tension, you treat it as if they're glued together. So if I had two masses glued together, they'd be moving with the exact same motion. That's happening here. Remember, what does a cord or rope do actually? It pulls on both ends. So one force feeling is the same as the tension in the other part of the line. Now, the other part to recognize is that the real key to a pulley or a rope is to redirect the force. Redirect. For example, when you see people turn around, take a quick look, you see them cleaning the windows, right? And you see sometimes the device that they're all standing on will go up and down, right? Well, there's a pneumatic device that's literally pulling on one of the lines, and by pulling down on this line, what does it do? It lifts up because there's a pulley at the top. So a pulley and a rope together are really just used to redirect the force. That's all that's happening here. So block H is clearly pulling down on the rope.
In that system, wouldn't the accelerations always be opposites, though, because one's always going to...
Well, they're different directions also, Matt. So altogether, we're going to say that this acceleration is a negative y direction. This is in the positive x direction. So this will be positive when we do some of the forces in the x. This will be negative acceleration when we do some of the forces in the y for this block. But we're going to look at some of the forces in both directions for both blocks.
So, like, in terms of, like, Newton's first law, the force pulling down the block would be due to gravity. Or, like, the force pulling down with gravity, and the reaction to that would be the tension of the rope pulling up.
Correct. But we don't know if they're going to be balanced because, again, if one exceeds the other, then it's going to be accelerating down. And that's going to be the goal to this problem, I think. Yeah, find the acceleration of the block, the acceleration of the other block, and then find the tension in the core. Those are the classic three things you're going to look for: is tension, and acceleration.
I was just thinking, like, so this is like a problem without friction. But I guess in real life, where there is friction, like the mass that's hanging would have to overcome the frictional force.
What frictional force?
If there was frictional force, I'm saying, right?
If it were against the wall or if air resistance were there, yes, both of those things. But the one that's sliding has kinetic friction between it and the floor if there were friction involved. And that would involve the x direction for the block S, and it would be in the y direction for block H. The frictional forces is what I'm saying, yeah. So let's start this problem like we do all problems. What do we always start force problems with? Yeah, free body diagram. So let's take a look at block S first. Block S has tension acting to the right. I call it FT. You can call it capital T. That is fine with me. I have a tendency to call it FT, so I'm going to continue with that nomenclature. I'm then going to write the weight, or FG, and this I do write FG, and they're calling this FGS for block S, and that's fine. And then FN acting up. If there was another block on another surface, I would have called that FN1 or FNS, meaning the normal force on block S. But because the other block does not have a normal force, we don't have to worry about the actual other block or naming FN with 1 or 2. Then for block H, we've got the weight of block H pulling down, and we've got tension pulling up. So this diagram in this first problem in your book gives you the free body diagrams, literally, right? We're just redrawing them with dots. So they're on the diagram, right? If you notice, they're all on the diagram already. Now, we know that we're going to call one of the masses M, capital, and the other lowercase. So let's actually specify those then. It's not very clear, actually. Let me do it this way, hold on, so you can see it better. Okay? Capital M for mass of block S, lowercase m for block H. Now, once we've got the free body diagrams, these problems are not, you can't see it, but it doesn't matter at this point. These problems are not really difficult because there's only one equation. If that's not clear to you, if that hasn't sunk in yet, write that down also. You're only ever going to use F net equals MA. F net equals MA. It's always going to be the same equation. That's the nice part about Newton's laws and dynamics, whereas with kinematics, we had many choices to make. The problem could have changed each time. No, there's one formula here. One governing formula. And then from there, we're going to replace certain things. So let's go ahead and start writing those governing formulas. So for mass M, the sum of the forces in the y direction equals ma in the y direction. In the y direction, I've got Fn pulling up. I've got the weight of block S pulling down, and that equals may. That's the y direction for the first block. Does it say anything about this block coming off the surface? Do you think it's going to come off the surface based on the way tension is pulling? So what can we say? The way tension is pulling shows me that it's only pulling it to the right, correct? It's not like it's pulling it at an angle like when you lift on like a sled. Remember, if you attach a rope to a sled, the sled might come off the ground, right? Because you're pulling at an angle.
F nat y is 0.
Good. So this is 0 because AY has to be 0 for the first block. It's not accelerating up or down. It's in vertical equilibrium, vertical translational equilibrium in that case. So this becomes 0 in this problem here. Again, because AY is 0 for the first block. Is that going to be the same case here? No. This one is accelerating downward. I can tell you that already because this block is going to be pulling down on it. Or it's at rest. It's one of the two, but it's not accelerating upward. There's no way that block S is just magically moving to the left. Block S cannot move to the left because there's no force pulling it to the left. So this block either has to be at rest or accelerating downward. It's one of the two things, but it's not accelerating upward. But the first block, I know vertically, is in a state of equilibrium. So does that do anything for me? Fn and FGS, they're balanced. All it tells me is that I can move this over, right? That's all it really tells me.
It also tells you that it's moving to the right because there's only one force acting on it.
Good. We know it's moving to the right. How come? Because there's no what?
There's no like equilibrium horizontal.
What would it be normally?
Friction.
Yeah. There's no friction in this problem, right? So Spencer said, hey, you know what? Because tension is the only force acting to the right, there's going to be horizontal acceleration on this block for sure. Because there's nothing pushing back. So it's got an unbalanced force, then unbalanced forces create changes in velocity. Remember Newton's first law. Equilibrium means the velocity is either constant or the velocity is 0. The minute you have an unbalanced force, it creates a change in the velocity, aka an acceleration is what it creates.
If we go to diagrams, if the forces are equal, do you want us to like draw a line so that they're congruent?
To say that there?
Congruent with vectors.
Meaning Fn and FGS you're talking about?
I can't remember if we did that last year.
I don't think I did. You mean like cross them off to show that they cancel?
Draw like a congruent line, like if you're doing geometry, show the lines are equal.
No, the free body diagrams on the exam, the length of your vector and stuff, they're not going to be, they're not going to be analyzing, is the length of this one the same as that length? No. But this formula, this will tell us that. Yeah. So this, all we gain from this formula is that Fn, all we gain from this formula is that Fn is equal to the weight of block S. And I gain that information simply by adding this over to the right-hand side. Well, just so we know, how do we designate weight? The weight of an object, what's the formula for that? mg. And the first block was capital M. So this is the formula, or this is the result we gain from some of the forces in the y direction. Remember, the block S has mass capital M, so it's capital M times little g, and that is the weight. Remember, people, that this g value is 9.81. It is not negative 9.81. If that's not clear to you, you need to recognize that. This little g here is 9.81, or 9.8, whatever. But it's not negative. The negative is already accounted for. Do you see it right here? That's where the negative plays a role already. We've already recognized that gravity is pulling it down. This g is the magnitude of acceleration, which is just 9.8. This is where the negative already came into play. Now, the x direction for mass capital M. Let's take a look at the x direction. I want to make sure I'm off the screen. Okay. So we have the sum of the forces in the x direction equals max. 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 That happens a lot, I'm sure. Calculus, right, by now? Okay, so what's acting in the x direction? Only tension, and it's acting to the right. So tension equals max. Now, that m, because it's the bigger mass, I should be using a capital M. Agreed? This is the bigger mass of the two. So when I'm doing these formulas, I should be consistent and use a capital M and a capital M. Even back here, even though we crossed it out and it didn't matter, I should make all of these capital M's because I'm looking at the larger of the two masses first. So this seems like there's information, but if I look at this, Chip, how many unknowns are there in this equation? How many unknowns? 2. So can I solve it? Not yet. Very good. Right now I can't. M is known, but acceleration and tension are not known. And that's what we're trying to find, right? Acceleration and tension. So clearly we're going to need another equation. Does this help me right here? Unfortunately, it doesn't. Because Fn is only useful if we're using what? Come on, you can answer this question. Fn is only useful when referring to friction forces. Are we doing anything with friction right now? So Fn doesn't really help us to link stuff together unless there's friction involved. Keep track of that. Okay? Fn doesn't really help us too much. So,
You said big MA equals small MA.
what we can do actually first, though, is look at the free body diagram and the equation for the second one, and we'll see if that results. But let's start with that before we do that. So looking at the second mass, for the second mass, so that was the first mass right there. Now for the second mass, I've got the sum of the forces in the y direction equals little m ay. So I've got tension acting up, the weight acting down, and that equals little m ay. The weight acting down is mg. I'm going to use little m because I'm on the smaller mass now. And there's my equation that I can use. So now I've got two equations right here. I've got those two equations right there. So unfortunately, it still looks like I have three unknowns until we recognize that first statement that I made to start today. So right now it looks like what's unknown? It looks like tension, AX, and AY. Again, I'm only using these two equations right here. Tension is unknown, AX is unknown, and AY is unknown. Everything else is known. M, G, those are all known values. So AX and AY are the problem right now, right? That's the issue. So how can we somehow make it work?
AX and AY have to be the same.
Give me more than that. You're right that they're the same magnitude, M. They're the same magnitude. You want to go a little bit further with your statement then? I'm telling you that the same value, this is pulling to the right, but this is pulling which way?
Down.
So this is going to be really negative A.
Yeah.
You follow what I'm saying there? So the acceleration of this block moving to the right, the first one up here, is, we'll call this A. So if the value of this is, say, 3 meters per second squared, this value must be negative 3 meters per second squared because it's pulling down. It's accelerating downward. So what we do is, we instead of using AX and AY, we say what Emily said and call them both A, but for the one that's moving up and down, we call it negative A. Spence, sorry, go ahead.
I was just thinking, so the acceleration, the vertical acceleration for block S is 0, and the horizontal acceleration for block H is 0.
Correct. In block H, I didn't do the horizontal because there's no forces.
And then the magnitude of the
Accelerations are the same.
equal.
But this is negative because it's going down. This is positive because it's going to the right. So now my governing equations are right here underlined in red. And now we can see that Ft and A are the only unknowns. Two equations, two unknowns, we're going to solve. Again, you can solve it in your calculator if you want with a system. You can plug in for big M and little m. But this is the kind of problem that's probably actually nice to solve algebraically so we can see the significance of our answer. So I'm going to slide this up a little bit. Okay, and what I'm going to do is I'm going to substitute for tension in the other one. So I'm going to take this expression right here and plug it in for tension right there. And the key is to recognize is that if you have one rope under tension, the tension it feels on both ends is the same. Ft in the first rope, Ft for this rope is the same throughout the entire rope. If I were to physically measure how much force is pulling the rope at any little fiber along the way, it will be the same the entire time. So I can replace that Ft with capital M, little a, and then the rest carry over. And then if I'm solving for acceleration, which I would be in this formula, I'm going to move things around a little bit. Looks like I'm writing mama. I know, right? And then I'm solving for a little a, so I'm going to factor it out. Emphasize the capital and the lowercase m. We'll call them M1 and M2, either way. But make sure you emphasize it. And then as a result, our answer for A turns out to be mg over big big M plus little m. Okay, that's a little m right there. I should maybe make that a little more clear. The numerator is a little m there. I make my little m's bubbly and the capital M's more rigid or angular. Okay? So that's the acceleration. And we can get a number because we have everything here. The number doesn't matter much though. You guys know that already, right? The number really doesn't mean much. And on your exam for multiple choice, I guarantee you the answer would be left like this. It would not be given as a number. Okay? It would not be given as a number, and M1 or big M and little m would not be given as values. Instead, you would solve this algebraically. But how does this help us? Let's think for a moment. Ready? Watch this. This is going to blow your mind. It really should. What if the first block, the one that's on the surface, the one that's sliding left to right, what if that block weren't there? What if the block sliding left to right just weren't there anymore? What would happen to this block? It would just, what acceleration would it fall with? Okay, take a look. Cancel out big M. You're left with little mg over little m. What happens to little m's? And what are you left with only?
G.
9.8. The significance and the power to an algebraic solution is so obvious by looking at this. Literally, if the big block didn't exist, the answer would just become g. The m's would cancel there, and you would get just g. That's why we're solving algebraically, so we can understand the problem. Okay, so we can understand it. What if the little block didn't exist? Would the upper block move at all? Because nothing's pulling down on it, right? Okay, look. The little block doesn't exist. So what does little m become?
0.
So this whole thing is 0 over some number, which is 0. Very good. It's just 0. It's not a trick question. So the acceleration would equal 0, meaning this block would not slide to the right anymore if the little mass wasn't there to pull down on it. So the significance of the answer and the value makes so much sense when we look at the algebraic solution. Take a look at that. When we look at the algebraic solution, guys, the algebraic solution is so powerful. Now, if I want the tension force, here's what I'm going to do. I'm going to take this answer. I'm just going to plug it back in for acceleration up there. And let's do that. We get tension equals big M times the acceleration. And there's the tension force right there. Okay, there's the tension force right there. I'm not going to discuss the tension force at all, maybe for a moment. What can we do with this one? I mean, we could say the same concept, right? Everybody see the same concept? If the big mass didn't exist, take a look. The big mass didn't exist. 0 times anything is, so would there be any tension in the rope? No, because there's nothing pulling back. If the little mass didn't exist, this becomes 0, and then again, 0 times anything is still 0. So the point is, if either of these masses weren't there, the rope would have no tension, which makes sense. If I just drop something with a rope off the end, the rope's just going to be doing this, right? That's all it's going to be doing, like a fishtail. It's not going to actually be pulling. It's not going to be taut. There's going to be no tension in the rope. So whether either of these if either of these masses were 0, tension automatically becomes 0, according to my algebraic solution. Okay? Again, the numerical part doesn't really matter. In case you're wondering, so you wanted to know maybe, the numbers would turn out to be 3.8 meters per second squared for acceleration and 13 newtons for tension. Okay, but again, you could go ahead and practice and go through this whole process if you don't believe that part. Let's go on to a second problem. Okay, this is going to be... Where are we? Oh, I know it first? Yeah, I do. Okay. This is going to be problem 5.04 on page 110. This is going to be 5.04 on page 110. Just give you guys the figures so you can see it.
Why does it specify that it's a box of sea biscuits?
This book has a tendency to do that. You notice that?
They have the weirdest examples.
What was that?
It was like a homeless man. It was like,
No, it's like
Wait, I have it. A hoodlum. It was a hoodlum throws a stone.
What does it say? A hoodlum?
A hoodlum
Throws
throws
a
a
brick
stone
through a window.
vertically downward.
You know, that's not very PC either, right? To use the phrase
Or-
hoodlum. It assumes that people from what is called like the hood would.
A bicycle, and then in parentheses, human-powered vehicle.
In case you know what it is, right? Okay.
Foraging for trash food.
for trash.
What was that?
A skunk foraging for trash food.
Nice. For trash food. Alright. Alright, so in figure 5.15a, a cord pulls a box of sea biscuits up a long frictionless plane. Inclined at 30 degrees, the box has a mass of 5, the force from the cord has a magnitude of T equals 25 newtons, and it says what is the box's acceleration A along the plane. So this problem becomes tricky because it's on an inclined plane. And actually your book starts by saying this, and this is no joke, I'm reading this. Many students consider problems involving ramps, inclined planes, to be especially hard. This difficulty is probably the visual part because we work with a tilted coordinate, all this stuff. They're pretty much trying to set you up like saying you can't do it. Trust me, it's not hard. It is not hard. I'm going to go through something right now that will show you how to remember how to work these problems every single time. And you don't have to derive it any time. So let me go with starting first with a free body diagram. So I'm going to start with my object right here. I'm going to start by first putting tension coming from that cord. I'm then going to put a normal force like this. And then I'm going to put weight like this. And there's my free body diagram. The issue becomes the fact that nothing or not everything is perpendicular. That's why the book says it becomes a hard problem. So let's talk about this FG value here. The FG value is the one that I'd rather break up. Because if I think about this, well, FG is acting straight down, Mr. Howell, and the Y direction is down. But then FT and FN I have to break into components, right? I don't want to have to break up two forces into components. And clearly FT and FN are both angled. But I don't want to have to break them up into their X and Y values. So here's what I do. I start by tilting my axes. So let's go ahead and call this the Y direction. And let's go ahead and call this the X direction. And traditionally, down the ramp is considered the positive X direction. So not only are you tilting your axis, but you're kind of flipping your X-axis. So again, for the X direction, we're going to consider down the ramp to be positive in the X direction and up the ramp to be negative in the X direction. So because of that, what I need to do really is recognize that FG really pulls like this and like this. That's what FG is really doing. And notice what I did. I made a little rectangle. Turn your head, please. You'll see that this and this becomes this as hypotenuse. Think of like the X component, the Y component, the overall weight. So this is the X component, this is the Y component itself. Now, it turns out that the X component is always going to be FG sine theta, not cosine. That's where it gets tricky. And the Y component is always going to be FG cosine theta. So if you recall what I said, I don't know, a couple days ago, we can't have both the overall force and its components on the same diagram. Remember I said that? You can't draw both things on the same free body diagram or it's redundant. FG and those two blue components are the same thing. So I can only have one of them on my free body diagram. The one that's more important is the one in blue. So now what I'm going to do is just go like this. I'm going to say to myself, oh, that's gone. Okay, there's no longer weight pulling straight down. I broke it into its components. For the sake of time, I mean, it depends on last year, but you may have seen this last year, you may not have. For the sake of time, I'm not going to get into the derivation. It's on that same page that this problem is on. It shows you where cosine and sine come from. So this is all on page 110. So if you want to see that, you can look it up. But here's what you have to know. Inclined planes simply use this angle theta and switch sine and cosine. Normally, for the X component of something, you use the cosine. And for the Y component, normally you use the sine. For inclined planes, simply switch them. It really doesn't matter the derivation about why that happens. It really doesn't right now. And for the sake of doing well in this test, I want you guys to just recognize that switch your cosine and sine for inclined planes. Now, that is not, by the way, take a look at my diagram real quick. Look at the figure. If I had a force acting like this at a second angle, theta 2, that is not the same for that force. To break up this force, you've got Fy, which is F sine theta 2, and then Fx is F cosine theta 2. It's only for weight that we do this. Is that clear what I'm saying? It's only for weight that we do this. So it's not a generalized thing. I don't want you to be like, oh, no matter what angle it is on an inclined plane, I'm going to switch up cosine and sine. It's only for Fg, when we break it into components, that we switch cosine and sine. Now, with that said, this becomes an easy problem now. We simply look at the x and the y direction. Sum of the forces in the y direction tells me Fn, oops, let me put like a colon here, tells me Fn minus Fg cosine theta equals MAY. And that goes to 0. Again, why does AY go to 0 in this problem like the last one? Why did AY go to 0, Chip?
It's not coming off the
Ramp.
ramp.
Very good. It is not levitating off the ramp. The rope is pulling it up the ramp, not off the ramp. The rope or the cord is pulling it up the ramp. Then we look at the x direction. And in the x direction we've got, remember, down the ramp is positive now for these problems. So we've got Fg sine theta acting positively because it's down the ramp. We've got the tension acting up the ramp, so that's negative, and that will equal MAX. Now, if the tension is equal to Fg sine theta, if these are equal, what do we know about the problem? These values are equal to each other. What would we know about this kind of a problem, Chip?
I was going to say, you said that side equals 0.
Which tells us what? If this whole thing is 0, what must be 0 over here? S can't be 0.
Acceleration.
So when these are equal to each other, what state are we in?
Equilibrium.
No, we're in New York. Yes, we're in equilibrium. We're in a state of equilibrium. So in a state of equilibrium, we know that the acceleration is 0. So this will become 0 if these were balanced. But this problem says determine the acceleration of the block. So there's a good chance it's not going to turn out to be 0, but let's figure it out. Let's go ahead and figure it out. So does the y direction help me at all? Do I need the y direction? Let's see, what do we know? In the problem, we're given tension is 25. Okay, that's good, I got that. We're given the mass is 5. Fg sine theta is really just 5 times gravity times the sine of the angle. So yeah, in this problem, I don't need the y direction at all. Everything I have is in the x direction. Fg is just mass times gravity. That's these two. Sine of theta is sine of 30 degrees. Minus the tension. Tension is given as 25 newtons. The mass is 5. Solve for AX. Solve for AX. And AX will turn out to be, what's the number? 0.1. Now, like last problem we had, it's really more important to get the algebraic solution. So let's do that. This becomes mg sine theta minus ft all over m equals ax. Okay, circled over there on the left is really the more important solution right there. And what does this tell me? Let's go through the process. This really does actually tell me a lot. Right, the number's great. Yeah, this is great. Okay, awesome, wonderful. And actually, this number would be negative, right? Should be negative because it's up the ramp. Or would it be down the ramp, actually? Let's see. Which one is greater? I'm using the book. I don't know if they consider up the ramp negative. Sine 30 is 1/2. 5 times 9.8 is around 50. So 49. It'll be negative 0.1 meters per second squared. Yeah. It'll be a negative here. Right down a negative here. I jotted down right there. Matt.
I also know why acceleration if it's going down.
Because remember, look at my axes. We tilted them, didn't we?
Uh-huh.
So look at the y-axis. The y-axis is this, right? See the y-axis right here?
Yeah.
So is the object literally accelerating this way ever?
No.
Is it accelerating this way ever?
No.
So AY is 0. Remember, it's the acceleration along what we are calling the y-axis, which in this diagram is tilted a little bit.
So, but that would also apply when it's on the ramp. Yep.
What do you mean?
So like it'd have an acceleration of 0.1 in just the picture of the box.
So this acceleration right here,
Yes.
right here, means that it's going up the ramp like that. It's literally being pulled up the ramp.
Yeah.
Because down the ramp, we're considering the positive x direction.
Yeah.
And since we got a negative answer, it must be accelerating up the ramp. Not off of the ramp, up the ramp. Off of the ramp would give us AY. Off of the ramp would give us AY. Up the ramp is AX. Or down the ramp is AX. Okay? For inclined plane problems, there's almost never going to be a problem where it lifts off the ramp. It's always going to be acceleration along the ramp. Some textbooks will even call this the parallel acceleration, meaning parallel to the ramp, versus the perpendicular acceleration, meaning perpendicular from the ramp. I don't think there's a need to use parallel and perpendicular if we just call the axes x and y and tilde.
I was thinking because there's a change in y value, like what would that translate? Just like negligible.
What change in y value?
Because it's going up the ramp, delta y is there's a delta y.
No, it's not. It's only delta x. Up the ramp is considered the x-axis. See, what you're missing is the tilted axis part.
I can't connect. I'm having a hard time like translating the tilted axis into like the real life scenario.
Well, here's what you do. You think about, okay, the x-axis is only this way, right? And our object either can go this way or this way. So we can only travel along the x-axis. Even though I get what you're saying, by seeing something move this way, you think, oh, it moves right and it moves up, right?
Mm-hmm.
So you think, oh, there's vertical acceleration. According to our diagram, we're considering the vertical this, and therefore there's only horizontal acceleration. So if you want to call the ramp portion parallel and call this perpendicular, you can put a little perpendicular symbol and a parallel symbol if it helps. Some books have done that in the past. I don't do that traditionally, but you can if that helps you. And let's talk about the power of this answer though. Again, the acceleration is a function of a couple of things. The mass, the tension in the rope, and gravity, the rate at which it's going, and the angle too, actually. What does the sine function do? As you go from 0 to 90, what does the sine function do? From 0 to 90. Think about it. What does the sine function do as theta changes from 0 to 90? Sine of 0 is 0. Sine of 30 is 0.5. Sine of 45 is 0.7071. Sine of 60 is 0.866. Sine of 90 is 1. What's happening to all my values? They're getting bigger. So if I increase theta, this quantity is going to get larger and larger and larger. Which, if I think about it, if I keep increasing theta, I'm going to get a larger value over here in the answer. Well, that means that it might accelerate down the ramp. This number turned out to be less than this number when we plugged in. This was like 24 point something. This is 25. So this number is a little bit smaller than this one, which is why our answer was negative in the first place. But if I keep inclining this, eventually I'm going to get to an angle where the force pulling up is not enough to pull it up. And it's going to start to do what? It's going to start to slide back down. Because this value, remember, this value right here is this, the weight of the object pulling down the ramp. If the weight of the object pulling down the ramp exceeds the tension pulling up the ramp, it will slide down the ramp. In our problem, tension was greater than the weight pulling down. This number, let's actually get a number for this. Let's do 5 times 9.8 times 0.5. 5 times 9.8, 5 times 10 will be, so... $24 point something. 5? Okay, thank you. I'm like having brain fart math in my head here. So that's what we have. That's what the numerator is. This is 24.5 minus 25. So if I change theta now to be 60 degrees, this number gets a lot greater. 9.8 times 5 times the sine of 60 degrees. And what do you get for that? Seems like 30, 40?
42.
Yeah. So we get a number like 40-something minus 25, which means now the weight pulling down is more than tension pulling up. So if I keep making theta greater and greater and greater, eventually this number gets greater than this number, which yields a positive answer for acceleration, which means it slides down the positive x-axis down the ramp. So the values matter a lot. Again, if I change tension, the more I make tension, the faster it's going to accelerate up the ramp. You'd be like, if I'm just pulling it even harder, it's going to accelerate faster up the ramp because this number is getting greater and greater. And then the mass is hard to discuss because it's in both spots. We could technically cancel these out and put this ft over m, but that's not really worth it at this point. Okay? All right. There are a lot of problems in this section. Okay? There are a good amount of problems. I still want to do a couple more. I want to start one right now. I know we only have a couple minutes left, but I do want to start the next one. And it's an interesting question. It really is. So the first time I looked at it, this is that page. So the first time I looked at it, I was like, ooh, this is intriguing. And then I read through it a little bit, and I was like, okay, I could see why it's actually important. There's one. And then here's the diagram itself. So the problem is an example that's very intriguing. What it's giving us is it's giving us a graph of acceleration instead of the actual acceleration because the acceleration is no longer constant. Okay, the acceleration is variable in this problem. So that's what we're noticing here. The problem begins with a certain amount of acceleration and continues to decrease over time as theta changes. So it says an example where you must dig information out of a graph, not just read off a number. In 516a, two forces are applied. The one force, two forces are applied, our friction is 4, but only one force is indicated. That's F1 right here. It says that force has a fixed magnitude but can be applied at an adjustable angle. So this force, the angle can change depending on how you're pulling on it. F2 is a horizontal force and is fixed in both magnitude and angle, meaning it's not going to change. So F2 you could either draw this way or you can draw it this way. The angle is not changing there. And it's horizontal, so I know that it's got to have an angle of 0 degrees. Figure 516b gives us the horizontal acceleration of the block for any given value of theta when theta ranges from 0 to 90. And the question is, what is the value of acceleration of A for when theta equals 180 degrees? So there's a lot going on in this problem. So when we start this problem, it's really important to start by saying to ourselves, our free body diagram is this. F1 at an angle of theta, but F2 for now has to be horizontal. So I'm going to start by calling this F2. Yes, I know F2 could also be acting to the left. Horizontal means either all to the right or all to the left. It's one or the other. So I could draw my vector for F2 either all to the right or all to the left. I'm going to draw it to the right. And if my answer for F2 turns out to be negative, it means I drew it the wrong way. It means that the force should actually be flipped around on the other side. So for now, though, I'm going to draw it to the right. And what this does is this allows me to have one governing equation. Here it is. Ready? F1 cos theta plus F2 equals MAX. And this is from the sum of the forces in the x direction. The y direction doesn't give me anything at all in this problem. Okay, the y direction is not what I'm going to be focused on, just the x direction. So you guys have homework obviously due in 2 days. I'd love for you to practice the rest of this problem. And you can check your work because the answer is all worked out for you on page 111 to 112, I think. Yeah. I think it ends on it ends on 111 at the very bottom. So I'll give you a hint. This graph specifically points out two locations with an angle of 0 and an acceleration. With an angle of 90 and an acceleration. If you plug in an angle and an acceleration twice, you'll get how many equations? 2. And how many unknowns do you have? 2. So I recommend that you finish this off over the next 2 days in a long or in conjunction with homework from 5.1 and 5.2. Okay, 5.1 and 5.2. 5.3 homework is going to be over the weekend. Okay, it's going to be over the weekend once we finish 5.3 on Friday. That's what 5.3 homework will be. So just keep this in the back of your mind. Okay, I have office hours right now, so you're welcome to hang out. If you have questions, just chill, relax. If you want to ask me any quick questions or anything lengthy, feel free to stay for a little while. I'll be here the whole time. Oh, the last thing I got to point out. Sorry, one more thing. I forgot to say it. We got to really push ourselves not to be doing like homework due on the day of in the recitation. And this is not Alex ratting anyone out at all. This is me being very, very like annoying to Alex, saying, "Hey, I really want to know like what is everybody doing every single day in recitation?" So today he said that some people started the 5.1, 5.2 homework as I suggested, but most were finishing up their lab that was due today. Try to get your work done before you come to school so that you can really utilize that recitation period to practice and go through problems. Again, this is not to everybody, but this was a general consensus. So I'm really pushing you guys. When you come to those recitation sessions, be ready to either start new problems or review work. But try not to think of that period as like, well, this is a period I can get work done, let's do the same day. Does that make sense? Yeah. Or else I'm going to have to stop making these due on day 5 and I'll have to make them due on day 4, which I don't really want to do. Okay? Does that make sense what I'm saying?
Yeah. Thank you.
Have a good day, guys. Somebody's projectile launcher's out still. Anybody know who that is?
Let the mouse on the
Whose is it? Can you guys find cabbage and stuff?
Yeah, we had it in there, but we were using it yesterday just to verify the data, and I didn't have time to do that.
No problem. When you get a chance, thank you. Oh, good. Cool. I just wanted to make sure I was glad.
Yeah, we're fine.
Based on anything from the year that we've covered already. So we'll never get into it. It'll always be something either that we covered the day before, the week before. Maybe there'll be a quiz on kinematics next week from last chapter or 2 chapters ago. So quizzes are just to keep you on your feet to get you tested and practice. Okay? Yep. Quiz.
Sorry, I can't cover the I'm still working, so.
I'm going to be here on Friday after school. I was going to originally be here tomorrow, but there's no way I can stay tomorrow. But Friday I will also. Because I was out yesterday, so I thought I'll make it up for you guys. I'll send an email about that today. Okay?
I was really cold in my basketball outfit. I practiced after, so I was like, I'll put on sweatpants so I'm not like freezing.
And I think I like that, you know. Just, it's like shorts are this big and it's the winter time. That's not comfortable, feeling awkward about it, right?
Yeah, we're assuming no air resistance, right?
Unless stated ever, the assumption is always no air resistance. Yep. Regina, anything to go over but not the quiz because George is taking it right now, but anything you want to review and go over?
Just the material.